let's very briefly review the floor function by looking at a couple of examples, numerical examples. Let's say we're interested in taking the floor of 9 over 4. Yeah, you may have heard of the floor function more commonly, or used to be called the greatest integer function. Confused a lot of people. But anyway, just operationally, the floor of 9/4 is equal to 2. Since 2 is the greatest integer that is less than 9 over 4, 9 over 4 being 2 1/4. Okay, now let's just see what happens. This is the part that kind of eluded me when I first learned about this function. Let's just switch the sign here. Minus 9/4. Okay. Now, my first impulse without giving it much thought was the answer is -2, right? It seems like, well, okay. But remember, that's not the greatest integer. See, 2 is the greatest integer that is less than 9/4, but in that very same sense, -3 is the greatest integer that is less than minus 9/4. Okay, so that's a little slippery, but if you give it some thought, think about this greatest integer and just on the left side. It just has to do with the geometry of the real number line, I guess. But in any event, this is a couple of examples, hopefully illustrative examples of what we mean by the floor function. Now we're trying to find the last 4 digits of this expression here, which would probably be impossible to compute by hand. So let's move along and look at an approach here. Now, this is a strange looking setup. I've heard people say that higher mathematics is about adding 0 in a clever way. If you notice, all we've done is add 0 here, 11 raised to the third power minus 11 to the third. The motivation here is that you can rewrite this very first term as a cube, namely 20 to the 39th cubed. And that puts it in a very well-known algebraic form called the sum of 2 cubes. Okay, so we'll write it like that, 20 to the 39th power cubed. Okay, and you'll notice we have the form, and I'll just go down to the next line to avoid the clutter. On the very next line, I've just rewritten this as we described here. Notice that this is in the form a cubed plus b cubed. But again, that's a very well-known algebraic structure. There's a ton of identities, a to the n plus b to the n sort of identities. All right, so anyway, carrying on, you can see that a cubed plus b cubed is a plus b. Okay, that's a plus b quantity times the quantity a squared. Now notice that if your a is 20 to the 39th, a squared is 20 to the 78th, 2 times 39, right? And this would be the minus ab part right here. And then, of course, this terminating term here, or this term right here would be b squared, right? Okay. Now that we make some progress with that because remember, we were trying to find the floor of the object, right? And so I switched back. I just didn't carry the floor through here. I put it back in right here. But notice that this factor right here will cancel with this factor, okay? And then you have minus 11 cubed over that factor. Okay, now let's keep going. You know, the floor function of an integer is an integer, so we can rewrite this as 20 raised to the 78th power. Notice these leading terms have tons of trailing zeros, right? 20 to the 78 has 78 trailing zeros. The term right after it has 39 trailing zeros. Okay, and then we terminate with 11 squared is 121. Now notice how what I did is the floor of any integer is the integer. For example, the floor of 7 equals 7. 7 is the greatest integer, less than or equal to 7. It's kind of a hassle just to even say that. But notice we did remove the floor piece here. Now we're going to have plus the floor of a negative number. A large negative number. Remember, a large negative number is the one closer to 0. Think about absolute value, I guess. Oops, that's 11 cubed. And then down here you have some large number, 20 to the 39 plus 11. That doesn't make much difference, does it? 20 to the 39 plus 11. But just like in our previous example, this is a large, some people would like to call it a small negative number, but it's a large negative number, all right? And just as before, that's going to make this equal to, this piece right here would just be -1, okay? This part right here would be -1, okay? In much the same way that the floor of -9/4 is -3, you drop down to the next smallest integer, okay? That's what we did right here. This is some very, I'll keep saying, it's a small and absolute value negative number, so to speak, okay? And so, but anyway, the floor of this object is -1. There's all kinds of trailing zeros here, 39 trailing zeros right here. So this leads us to believe, or I think it conclusively shows that 0, 1, 2. Now notice we would add this -1 because -1 is the floor of this object, right? Add it to the 1 and you get 0. So these are the last 4 digits, folks. 0, 1, 2, 0. And again, so a little bit of hand waving right here, but look, this is just padded with 39 trailing zeros right here. If you pop a 121 on, add 121 to that, you would have 38 more zeros in front of it, okay? So this is the last 4 digits, and it's a final answer. So let's, I'll just write it right up here. The last 4 digits would be 0, 1, 2, 0. And I think it's a cool problem because just imagine how hard this would be to do 20 to the 1/17th if you were doing it in kind of manual way. There may be some sophisticated way of doing it, but it's a huge number, but the algebra, you can leverage the algebra in a fashion, and then the properties of the floor function, and the answer pumps out fairly routinely. We didn't have to do a big calculation. The biggest calculation we really did was just 11 squared is 121. So if you think about that, it's pretty nice if this is the original task is to work with this. Now this is kind of a contrived example because if this wasn't this term cubed, I'm not quite sure what the approach would be. There'd be probably some other way, but it was designed to work out nicely because 20 to the 39th cubed is 20 to the 1/17th. Thank you for viewing.